Welcome guys, so we're going to start talking about evolution today, but before we really get into the process and the theory of how evolution itself works, we really need to sort of step back and talk a little bit about Earth history. So that's where we're going to start. And let's go all the way back to the beginning. So we know, based on geologic record, that Earth formed about 4.6 billion years ago. And the conditions on very early Earth were not anything like what we're seeing today. That early Earth was getting bombarded by rock and ice, as not only was the Earth forming, but so was the rest of the entire solar system. So all of this swirling dust and gas and rock and ice is flying around the disk of our solar system. And as this stuff continues to sort of bombard each other, some of it sticks, and eventually we end up with things like the planets. And for early Earth, from about 4.2 to about 3.9 billion years ago, we've got all of this rock and ice, and it's hitting Earth, it's sticking, it's vaporizing whatever water does happen to manage to settle out on the surface. So there really aren't any oceans, super hot, really thick atmosphere, not only with the water vapor that's getting literally vaporized every time we get hit with another celestial object, but also lots of volcanoes going on, so lots of eruptions happening, which is also spewing all sorts of chemicals, along with additional water vapor up into the atmosphere. So really not anything like what we see. Very inhospitable conditions. But after about 3.9 billion years ago, things in the rest of the solar system sort of have settled out. Most of the planets are formed, moons have been formed, and so we're not getting bombarded as a planet on a regular basis anymore, and so things start to kind of settle out, start to cool down a little bit. So a lot of that water vapor that is stuck up in the atmosphere slowly starts to condense. We start getting oceans that cover the vast majority of our Earth's surface, and a lot of this excess hydrogen that's also hanging out in our atmosphere finally kind of escapes off into space. And so we're finally going to set ourselves up about 3.9 billion years ago to potentially have conditions where life can start. So there's a handful of models that get thrown around in the early 1900s looking at, now that we understood basic geology and we understood the conditions based on that geologic record of what early Earth was looking at, we started to try and piece together, well, how did we get from this crazy inhospitable planet that was Earth at the beginning to all of this diversity of life that we see now? How did things get started? And one of the big models out there is this idea of the primordial soup model. And this was proposed back in the 1920s by two gentlemen, Oppern and Haldane, and really they were looking at the potential for how did we get from this inhospitable, crazy, chemically environment to actually getting organic molecules that could have started building pieces that resembled what we understood as life. And so one of the things that they're looking at is really that life would begin in those early oceans once they were able to actually form. That's what they were considering sort of this primordial soup. You've got all this water, and they're basically big solutions full of organic molecules. So in order for those organic molecules to form, they're talking big macromolecules like carbohydrates and lipids and nucleic acids. And remember that in order for those big polymers to get put together, I had to have smaller building pieces, aka monomers, to put them together, right? But in order for those chemical reactions to be these building processes, energy's got to become involved as well. Well, we also understood that early Earth's atmosphere not only was just full of these chemicals and water vapor, and we've got volcanoes erupting, but there was also a lot of intense weather systems, so lots of lightning, and we didn't have an ozone layer. There was no layer protecting us from the UV radiation that was coming from our sun. So these two gentlemen proposed that the energy to make those chemical reactions happen was already in place from things like that lightning and intense UV radiation. So they're putting this out there as a potential. There were the right elements on Earth, the right conditions in terms of the oceans, in terms of the weather, the intense UV radiation, to set up the ability for chemical reactions to start forming organic molecules in early oceans on Earth. It isn't until 1953 where two gentlemen, Miller and Urey, finally sit down and recreate those conditions in a lab setting and are actually able to produce some of those organic molecules, that there is any sort of credence given to that primordial soup model. And this is an experiment you definitely want to make sure that you are able to explain, so let's walk through it. So they're working in 1953, and they've got this setup that looks like this. Alright, so they've got a beaker here full of water and some other vaporized chemicals, liquid chemicals. This is their ocean. And they're going to heat it up because, remember, Earth's early conditions super hot, so it would have been able to be warm enough to actually boil the oceans to some degree, and so that's what they're showing here. And what they do is then trap that water vapor that's coming off of these oceans, right? And they're going to allow it to condense. And so they're going to send all that vapor up into our atmosphere. And not only is it going to be water vapor, but they're also going to have other things like CH4, hydrogen gas, NH3. These are all things that would have been coming out of things like those volcanoes. Okay? So this is our simulated atmosphere. Not only the water vapor, but all the other chemicals that would have been likely to have been found early in the atmosphere. They've also got electrodes in here to simulate things like the lightning and the UV radiation. Well, what happens over time, we know that as that atmosphere is able to cool off, things condense, which is what's going on here, right? Sort of like precipitation that we have happen. So here are your clouds, right? And as those clouds get saturated enough, eventually things cool off and condense and rain, and all that comes back down to the surface, and that's what they're ultimately collecting here. What would have fallen back into those early oceans as Earth cooled down. And what they were able to find is that down here in their collection beaker, they were finding all sorts of organic molecules, including things like amino acids, which we know are building blocks for proteins. So it seemed to support that primordial soup model now here in actual experimental data. And so this now gives that credence to our ability to say, well, yeah, it seems like there were the right types of chemicals, the right types of conditions, all set up on early Earth to give rise to those really early types of organic molecules that would have been necessary to get life started. There are other models out there. One other model that your textbook goes through is this idea of the bubble model, which came out in 1986. Similar idea, but they're talking now that a lot of those gases that were being trapped came from underwater volcanoes and happened to bubble to the surface, end up in the atmosphere, underwent those extra chemical reactions, and came back into the oceans. Like I said, similar idea to what's going on here with Miller and Urey. Okay, these guys don't necessarily give a particular place as to where these extra chemicals are coming from. So the bubble model sort of takes it one step further to say that we're pretty sure that those gases were coming from underwater volcanoes that were getting trapped and eventually ejected out into the atmosphere. But the basic premise is the same. We undergo those chemical reactions because of the lightning and the UV radiation, and things fall back into the oceans. This is more or less a model that most scientists at this point have pretty much accepted as probably how we got those early organic molecules. Just gives us a little bit more information than what the primordial soup model itself gave us. Okay, so we now have organic molecules, simple amino acids, simple carbohydrates, simple nucleic acids. What's the next step? Well, the next step in sort of evolving anything that looks like life today had to get us to the point of setting up some sort of cellular structure, right? When we talk about biology, the most simplistic version of any living thing is the cell itself. So those first cells, or even precursors to the cells, which is where we're going to start here, life had to have at least two major properties in order to really push forward, and that was the ability to have some sort of simple metabolism, right? Gain and use energy, have some chemical reactions that are happening in order to do that, as well as to be able to consistently and accurately replicate itself. So they think that we get these organic molecules that start forming in our oceans, and we end up having this spontaneous reaction where we get these things called protocells that start forming. And in fact, the AP biology kids are able to recreate and make these protocells in a lab right here in high school. And they talk about them as microspheres, coacervates, but pretty much what they are these combinations of abiotically produced molecules, right? So those proteins, those nucleic acids, those carbs that aren't actually being produced directly by anything living, but they're going to end up getting congregated and separated from their environment by some sort of membrane. And we can form these guys in a lab spontaneously by making lipid bilayers. So if I stick certain types of lipids into a watery environment, they're naturally going to want to spontaneously make that membrane structure that we talk about with a cell membrane, because they're trying to avoid making contact with that water. And in the process of doing that, they often end up trapping other molecules inside, and that's where this simple metabolism comes from. And so that cell membrane now sets up the ability for that metabolism to actually happen more effectively. Because if I can trap a couple of molecules in this environment and shield it from whatever else is going on externally to it, this process is going to happen much more efficiently because I don't have to deal with those outside forces. And those materials are going to be much closer together. It's going to be easier to get them to collide and break down with less energy and move molecules around. So that's really where this starts. So these initial microspheres, coacervates, protocells, whatever term you want to use, seem to meet those really early requirements of not only having a simple metabolism because they happen to trap these molecules in chemical reactions inside themselves, which now happen more efficiently, but they can also reproduce themselves. Alright, and so I can make more of those little coacervates from one big one, and in the case of what the AP kids do, it's simply a mild adjustment in pH, and they can make these guys sort of explode in terms of the numbers that they see under a microscope. So that's our first step. The other piece to this, in terms of that replication, and accurate replication, has to be some sort of genetic material. Alright, I have to have some way to pass on information from one generation to the next, so that each generation knows what to do. Well, how do your cells do it? Well, we do it via DNA. Okay, but DNA is a double helix, it's double-stranded, it's a pretty complex structure. So when we look at the genetic material that's out there, well, it's nucleic acids, so we've got DNA or RNA. And we are pretty confident at this point that actually RNA is the first genetic material and DNA eventually evolves from that. where are we coming up with that? What's some of the evidence-based information behind that? Well, first off, RNA in and of itself, single-stranded, so its structure is more simplistic. But we also have these molecules that still exist called ribozymes. And that's sort of what you're seeing here. So RNA is actually able to bend back on itself, create temporary short pieces of double-stranded RNA molecules, which we can then use as templates and make copies of. But the other interesting thing with the ribozymes is that not only can it act as genetic information, but these ribozymes can also work like enzymes. So they can catalyze and speed up chemical reactions. So all of a sudden, in a single molecule of RNA, I'm now meeting those two criteria that we just talked about back here. The ability to accurately replicate, because I now have a set of instructions to work with, and I now have enzyme-like capability to make that metabolism work even more efficiently than it would by simply putting a membrane around it and separating it. So we've now sort of met all of these criteria. Eventually, we think DNA came from just some breakage here in a double-stranded RNA molecule, ended up leading us to a double-stranded molecule, happened to be more stable, and so eventually DNA kind of evolves from those sort of double-stranded pieces that happened to break as it went.